Thanks, Mark. My name is Michael. I'm going to be talking about the properties and applications of activated carbon. Activated carbon is a powdery black flammable solid that contains what are called mesopores. These mesopores are pore spaces in the structure that range in size from 2 to 50 nanometers. Obviously, this is critical in determining whether or not to use activated carbon for purification purposes. Activated carbon is considered a spontaneously combustible material, or class 4.2 according to the Department of Transportation. The applicable RCRA code would be D001 due to its ability to cause fire and burn vigorously and persistently. Obviously, the application of the D001 code depends on the purity of the substance, as well as if the activated carbon was used to filter out another RCRA contaminated compound. I know here on campus, in my experience, chloroform is commonly used, or is commonly filtered out, by activated carbon. Moving on to density. Density basically ranges, with its pore space included, from 250 to 650 kilograms per cubic meter. If you account for what is called its true density, or a density accounting for the pores between the lattice structure, it ranges from 2,150 to 2,200 kilograms per cubic meter. And as the ratio of mass per unit volume increases, more unoccupied pore space is available for filtration. In other words, as the density increases, so does the efficiency, quality, and generally the price of the compound. Moving on to particle size, another type of property. It's similar to density. As it increases, particle size increases, so does efficiency. A larger particle size creates more surface area, allowing for a higher number of pores and a faster rate of absorption. The molasses number of activated charcoal refers to the size of the mesopores. The higher the molasses number, the larger the mesopores, and therefore the larger the absorbed molecule. The ash level of activated carbon describes the purity of the compound. As Mark mentioned earlier, activated carbon uses adsorption, not absorption, to purify or filtrate other compounds. Adsorption is a surface interaction. Basically what happens is the filtered substance is more or less physically captured by the activated carbon's pores. This is why it's critical to know the size of the mesopores in the carbon that you're using, as well as the size of the molecules that need to be filtered. So moving on to applications of activated carbon. As Mark said, the most common use of activated carbon is in water filtration. Publicly owned treatment works, or POTWs, frequently use activated carbon in their facilities for sewage treatment. Municipal potable water is often filtered through activated carbon to remove VOCs, and home water purifications products such as Brita water filters use a combination of ion exchange as well as activated carbon to remove metals and chlorine to enhance the taste of water. Activated carbon is also used in HVAC, or heating, ventilating, and air conditioning units in manufacturing facilities, offices, and operating rooms. Basically what happens is the activated carbon in these HVAC systems purifies the air from environmental nuisances, organic compounds, foul odors. In the food and beverage industry, activated carbon is used in a variety of ways. Basically, what was found in our literature was the decolorization of sugar, purification of certain foods, chlorine removal, and the decaffeination of coffee. It's also used in industrial applications, such as metal recovery. This is where we could find maybe a RCRA treatment storage disposal facility using it to recover metals such as gold. Filtration devices and tight-fitting respirators, such as a half-face or full-face respirator, use activated carbon to filter out harmful VOCs. And then it's also found in pharmaceutical companies to remove VOCs during production processes. It's also used in the medical world, maybe used orally for poison treatment. If you swallow some other toxin, they could give you an activated charcoal pill that will move through your system and hopefully remove that poison. And it's also used in odor control and wound dressing. And then our last application is in industrial and chemical hygiene. Here on campus we use this pretty frequently. And I actually have a little sampling pump with a filter at the end that is a glass column. This column in the sample pump, or what we refer to as an industrial air sampling train, is used by industrial hygienists and chemical hygiene officers to sample the amount of organic compounds during a given procedure. The flow rate of the pump is essentially set really low, less than 0.2 liters per minute, since the absorptive properties of the carbon are so highly efficient. Here at NAU, or Northern Arizona University, we use this apparatus throughout all the labs on campus to measure benzene, chloroform, naphthalene, several volatile, harmful organic compounds in the lab, basically to prove that no exposure has happened. We also use Draeger tubes on campus, and they have activated carbon. And there's some other sampling media in the industrial and chemical hygiene world that use activated carbon for basically exposure assessments. So, in conclusion, activated carbon is a highly useful spontaneous combustible material. In my personal experiences as a waste supervisor, it's always been shipped as a RCRA flammable D111 material. Any increase in its relative density or surface area increases its ability to purify other compounds. Obviously that depends on the compound, so you can't purify something that's smaller with larger sized mesopores. It uses the process of adsorption to bind materials in the mesopores, and those mesopores range in size from 2 to 50 nanometers. It's common in several different industries, including water purification, RCRA treatment storage disposal facilities, food processing, home water filtration systems, fish tanks, as Mark mentioned, and industrial hygiene sampling. Thank you guys for your time. I'm sorry, I'm not sure I will be available for questions. Mark said he's going to try and log in, so look for him. And here's our references. Thank you all.